Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series meant for BSc Honours Physics students. We have been going through a course of lectures on interference, and the phenomenon of interference depends upon coherence, as all of you know. And in this lecture, which has been entitled Interference and Coherence, I will be having the contents as given below. A relation between coherence length and bandwidth, spatial coherence, temporal coherence, determination of coherence length, and the condition for spatial coherence. So far we have been talking about the importance of coherence with regard to the experiments which we have seen in optics, namely Young's double slit experiment and the Michelson's experiment. In the Young's double slit experiment, in order to obtain stable interference pattern, we all know by now you would have 2 coherent sources. In reality, as I told you in the last lecture, there is nothing like a monochromatic source, or nothing like exactly coherent source, or a monochromatic, strictly a monochromatic source. There is no ideal monochromatic source. So we talked about bandwidth, coherence, length, and so on. By bandwidth, what we meant was the spread in the wavelength of a particular line, which we have been hitherto calling as a well-defined monochromatic line, which is not the case. So we pass on to obtain the relation between coherence, length, and bandwidth. You all know the relation connecting the frequency, wavelength, and the velocity of light. The differentiating the above expression, we get delta nu, the spread in the frequency of a band of a particular line or a band. And from the equations that we had earlier in the last lecture, we have C by L coherence is equal to C by lambda square delta lambda, and the coherence length ultimately becomes lambda square by delta lambda. And this means that the coherence length and bandwidth of the wave packet are related to each other. There is what is delta lambda, that is the spread in the wavelength, that is the bandwidth, and the coherence length, they are interconnected. The longer the wave packet, the narrower will be the bandwidth. In the limiting case, when the wave is infinitely long, we obtain a monochromatic radiation of frequency nu naught or wavelength lambda naught. If the coherence length is infinitely long, as I will be showing in the pictures to come, you have an infinitely long wave, you got oscillations contained, more number of oscillations, then the wavelength is well defined, this is a monochromatic source. If you have got only less number of lines, then the spread is very large. You see the spread coming down, ultimately the spread reducing to 0. That means a strict monochromatic source. So, the relation that connects your bandwidth d lambda and n. N is the number of oscillations. It goes as follows. If n is large, d lambda will be 0. The spread is 0. If n is large, number of oscillations in the wave train is large, your d lambda is 0 or delta lambda is 0. Delta lambda is 0 means what? It leads to lambda naught, a strict monochromatic source. So, the dependence of bandwidth on the length of the wave packet is shown schematically in this diagram that we have here. Now, coherence is an important property of light. I need not overemphasize. We talk of spatial coherence and temporal coherence. I told you in the previous lectures, in the case of Young's double slit experiment, if you want to get a stable interference pattern, then the distance separating the two slits should be small. If the distance is large, then you will be getting only noise, or that means you won't be getting a stable interference pattern. I talked about visibility of fringes in the last lecture. The fringes will not be visible. The fringes will not be visible if the distance separating the slits is large. So, the separation is large from the distance point of view, so called spatial coherence. From the time point of view, it is called temporal coherence. If I connect two timing separated by a time interval, then we will be having a temporal coherence. So, you should remember, in the Young's double slit experiment, you got two slits separated by some distance. Large means you won't be getting interference pattern. Small means you will be getting a stable interference pattern. So, spatial coherence is something associated with the Young's double slit experiment. On the other hand, the temporal coherence is the one which I told you in the last lecture also, is the one associated with the experiments which are performed by Michelson using his interferometer, so called Michelson's interferometer, in which case if the two mirrors which are held perpendicular to each other, M1 and M2, if the light were to pass through the same distance from the point to the mirror M1 to the point, from the point to the mirror M2, if these two distances are the same, then the time difference is 0. So, you will be having perfect circular fringes. On the other hand, the mobile mirror is moved in such a way that the distance that separates the point and M1, the point and M2 is larger. It creates, the distance is larger means what? It creates a time difference, or a temporal coherence will come into the picture in the case of Michelson's interferometer. And so, the temporal coherence is due to the time difference. You can have this as some sort of homework to be done. If you have got a light source, where will you have the points P1, P2, P3? If P1 and P2 are the points along the line, or P3 may be a point along the circumference of the arc, P1 and P3 will be at the same phase. That means that relates to the Young's double slit experiment. Then on the other hand, if there is a time delay, it is connected to the Michelson's interferometer, and a definition of monochromaticity. From the equation 11 that we had earlier, we conclude that the temporal coherence is indicative of monochromaticity. The degree of monochromaticity of a source is given by epsilon is equal to delta nu by nu naught. When will your delta nu become equal to 0? If the source is strictly a monochromatic source, delta nu is 0 means what? The frequency spread is 0. the bandwidth becomes a narrow line. If that is the case, you have an ideal monochromatic source. If epsilon becomes equal to 0, that means delta nu by nu naught is equal to 0 or epsilon is equal to 0, you get a strict monochromatic source. It is called monochromaticity. Monochromaticity means what? Your delta nu should be equal to 0. What is delta nu or delta lambda? The bandwidth should be equal to 0. So that means you have a strict monochromatic source. Yes, there is no spread. How do you define purity of a spectral line? The width of the spectral line is given by delta lambda. It is seen from the earlier equations, delta lambda will be equal to lambda square by L coherence. If L coherence is 0, delta lambda will be equal to 0. That means you have a pure spectral line. Delta lambda is 0 means you have a, spread is not there. Spatial coherence is called lateral coherence. Where do you come across spatial coherence? What is the experiment with which you associate spatial coherence? As I told you in the beginning of this lecture, the spatial coherence comes when two slits are kept either far apart or nearer to each other. That is space. The spatially, if they are located very close to each other, then only the two light beams will interfere. If they are far apart, there is no question of interference. The light will be going here, the light will be going here straight, and so you will have plane waves, plane wave fronts will be coming. So they will not be interfering. The schematic diagrams I showed much earlier also in the earlier lectures. Therefore, this is called a spatial coherence, otherwise called a lateral coherence, which comes when you are dealing with Young's double slit experiment. So you have them. I think it is not necessary that one can take this as a homework and do, where you will be having the points P1, P2, P3 in order that you understand spatial coherence as well as temporal coherence. Let me now move on to obtain a relation or how to determine the coherence length. Coherence length, as all of you know, is the length covered by a wave train. I told you about wave train or a wave packet. The length covered by wave packet L, that is known as the coherence length. The coherence length can be measured by means of again the Michelson's interferometer. I want you to recall the Michelson's interferometer. As you will remember, the interferometer is made up of essentially a partially silvered or semi-silvered glass plate. You got a source here, semi-silvered glass plate. You got a mirror here. You got another mirror. Can you comment about the two mirrors? The two mirrors are mutually perpendicular to each other, should be made to be perpendicular to each other in order to get circular fringes. If they are slightly inclined, one of them is inclined, then you will be getting a wedge-shaped film. You will be getting straight lines instead of circular fringes. And again, the distances covered by the two should be equal from the point, from the semi-silver glass plate, the distance traveled by light beam to mirror M1 and M2. If the distances are the same, then you will be getting circular fringes. One of the mirrors you will recall can be moved either towards the semi-silver glass plate or away from the semi-silver glass plate. By moving that through lambda by 2, you are introducing a path difference of lambda. All these things you know. So one of the components is passing through the semi-silver glass plate to the mirror M1, the other one goes to mirror M2. Let us have a break at this point. We will resume the rest after the break. Welcome back at the break. We have been trying to understand as to how the Michelson's famous interferometer can be used to determine the coherence length, apart from the fact that it has been successfully used to determine even the velocity of light, the distance between two stars, thickness of a glass plate, refractive index of a transparent medium, and so on. There are very many applications for the Michelson's interferometer. Apart from these things, as I told you, the coherence length is one that can be obtained. That is what we are precisely looking at now. And you know by now the construction and working of Michelson's interferometer. I told you that there are two mirrors. Through the telescope, one can see directly the light coming from one of the mirrors, M1. And if the mirror is M2 here, because the telescope is seeing the mirror M1, because of the mirror M2, a virtual image will be formed, M2 prime. M2 prime be the image of mirror M2. Where is M2? M2 should be the mirror here. There is a source here, the glass plate. M2 is the mirror here. M1 is the one that can be directly seen. So, through the telescope, you look at the mirror M1, that is directly observable. The image of M2 will be formed there. The virtual source or the image is formed, M2 prime be the image of M2 formed by G, and these two will be interfering, right? The light coming from M1 and M2, right? The light coming from the two mirrors will be interfering, and the interference pattern can be seen through the telescope T. If the reflecting surfaces of the mirrors M1 and M2 prime, the image of M2 are separated by a distance D. You know the distance D, what is D? D is the distance separating M1 and M2 prime. M1 is the mirror here, M2 prime is the image obtained for the mirror M2. So, they are separated by a distance D. Then we saw in the earlier lectures 2D cos theta and so on. The path difference and all we calculated. With the path difference we added lambda by 2 because of dissimilar reflection and so on. So, 2D will be the path difference, because if D is the distance separating, the mirror light comes and then returns back, because it is traveling upward, coming downwards. So, 2D the effective path difference introduced between the two interfering waves. The condition for fixed phase between the two waves 1 and 2 will be satisfied if 2D is much lesser than the coherence length. So, if 2D is much lesser than the L coherence, that is one condition. In such a case, distinct interference can be seen. Okay, what is the condition under which you will have distinct interference pattern? 2D should be much lesser than the coherence length. On the other hand, if 2D is much larger than the L coherence, that means if D is made large, I told you some time back when we were trying to standardize a meter, the distance between the two mirrors cannot be like 1 meter, right? When you want to standardize a meter, one of the mirrors cannot be, one of the mirrors is movable. I told you that the mirrors cannot be moved, and that is the reason why we used etalons. You can recall the usage of etalons to determine the velocity of light. The movable mirror cannot be moved by distance more than 10 centimeters. If you try to move, what will happen? There will be no interference pattern. The interference pattern will not be seen because the Young's double slit experiment, the distance separates the two slits should not be too large. If it is too large, there will be no pattern. Similarly, here in the case of Michelson's interferometer, the time difference or the path difference that is created by, you have one mirror, stationary mirror, the other is movable mirror. If the movement that has been exerted on the movable mirror, if it is very large, if that is very large means what? D is the distance that separates the M1, M2 prime. D. 2D is the path difference. If 2D is much larger, very large, then what will happen? You won't be having interference pattern. This should be borne in mind. In the Young's double slit experiment, the spatial coherence, here a temporal coherence in the Michel's interferometer. How do you produce temporal incoherence? It is because of the fact that the d distance through which the path difference introduced because the movement of the mirror, if it is too large, 2D is very large, d is large or 2D is very large, much larger than the coherence length, then again the interference pattern will be disappearing. If the phases of the two waves are not correlated and the interference fringes will not be seen. These things should be very well understood. It is important from the young students, you should go home and do the experiment when you have two slits very close, two slits far apart, and Michel's interferometer, the two mirrors are kept perpendicular to each other, separated by a distance d, the image is separated, the image and the mirror separated by distance d. If it is made, the distance d is made very large, then the interference pattern will disappear. I think there are things which one should try to do in the home, and if d is very large, the pattern will disappear. That is where you have to see where the pattern is disappearing. So that will decide your coherence length. To obtain coherence length of the waves emitted by a light source, the distance d between the two mirrors M1 and M2 is varied by moving one of the mirrors. As the distance varies, contrast of the fringes decreases and ultimately they disappear. You have to look for the disappearance of the fringes. That means you are crossing a particular limit. If the path difference 2D at this particular stage, where the fringe disappear or the fringes disappear, give us the coherence length. The coherence lengths for various sources are given here. It is 1 millimeter, it is order of 1 millimeter or 1 centimeter, neon red line 3 centimeters, red cadmium line 30 centimeters, red cadmium line, you will recall, it was taken as a standard line in the case of Michel's interferometer when he tried to standardize a meter. Orange krypton line 80 centimeters, and that of a commercial helium neon laser, the coherence length will be 15 meters. So the coherence length of light from some of the lasers will go up to a few kilometers. So the condition for spatial coherence, the degree of spatial coherence of a beam of light can be deduced from the contrast of the fringes produced by it. The broader the source of light, the lesser is the degree of coherence. In Young's double slit experiment, the slits L1, L2 are illuminated and it gives a uniform pattern. The absence of the fringes indicates that the spatial coherence is lost. I told you just now the loss of temporal coherence in the Michel's interferometer. Similarly, if S1, S2 are separated by a larger distance, then what happens? The spatial coherence is lost, right? The waves emerging from them having been derived from the wavefront division or coherent and stationary interference pattern will be observed on the screen if S and S2 are nearer to each other. So you have got the two slits S1 and S2, you have got a source here. The angle subtended here is 2 alpha, this is 2 theta. I will show some, for sake of completion, the angles and the relation that you have here. The path difference between the two waves passing the edges A and B of the slit S is delta will be B sin alpha. Distinct fringes will be obtained when delta is much lesser than 1 by 2 into lambda. Therefore, it requires B sin alpha should be much smaller than 1 by 2 into delta. This equation determines the size of the source which is spatially coherent to produce fringes of satisfactory contrast, and the equation 16 shows that the smaller is the size of the source, the better is the spatial coherence. The condition for spatial coherence is the light source should not be an extended source, it should be a point source. Spatial coherence of waves decreases with increasing size of the light source. Instead of point source, you got an extended source, then the coherence will be lost. So the 2 theta to and 2 lambda are the angles subtended as shown in the diagram here. You have the 2 theta and 2 lambda are the angles subtended by S1 and S2 or 2 alpha, and at the edges A and B it is 2 theta. So, you get a fringe pattern. The condition for no fringes is that you won't be getting fringes. 2 theta is lambda by 2d. When the slit S is wider, the edges A and B move away from each other. As a result, the pattern A prime and B prime also move away. When the maxima of one pattern fall on the maxima of the other, the fringes appear. Therefore, the condition for fringes is that 2 theta is lambda by d, or d will be lambda by 2 theta. In other words, there is a restriction imposed on the slits S1 and S2. D must be small compared to lambda by 2 theta. This is an important thing. The distance separating the 2 narrow slits which give rise to the 2 monochromatic sources, D must be very small compared to the wavelength lambda in order to maintain spatial coherence and to obtain a distinct, stable fringe pattern on the screen. Light produced by lasers is highly coherent. Therefore, when a laser is used as a source, interference of coherence fringes can be obtained without the aid of the slit S. So, the important point I want to make is as far as Young's double slit experiment is concerned, to obtain a stable interference pattern, S1 and S2 should be nearer to each other. We talked about 2 coherent sources. You have a source S. From that, you have got 2 slits, S1 and S2, which act as 2 coherent sources. They act as 2 coherent sources because light is coming from the same or a single original source. You got a source S and it eliminates S1 and S2. The condition for spatial coherence is S1 and S2 should be closer, or the distance that separates S1 and S2 it should be much smaller compared to the wavelength divided by 2 theta. That is the condition for spatial coherence. What is the condition for temporal coherence, which you come across in Michelson's interferometer? The condition for temporal coherence is a fact, namely, your D should be small. What is D? D is the distance that separates the mirror M1 and M2 prime. M2 is the mirror here. The image of M2 is M2 prime. The movable mirror and the stationary mirror, if M2 is the stationary mirror, the M2 prime is the image obtained for the stationary mirror, and the distance that separates M1 and M2 prime, that is the D should be small. So, here D should be small. This D refers to the distance that separates the 2 sources or the 2 slits S1 and S2, which act as 2 coherent sources in the case of Young's double slit experiment. Whereas, in the other case, D is the distance, as I told you, separating the 2 M1 and M2 prime. That should be smaller in the case of Michelson's interferometer in order that you get a stable interference pattern. We will now move on to the summary session. The spatial coherence is an important factor for obtaining stable interference fringes in Young's double slit experiment. It is a temporal coherence which is of significance in Michelson's experiment. The method of measuring the coherence length is explained. Condition for spatial coherence was discussed. The questions are: give the relation between the coherence length and bandwidth. What do you understand from the terms spatial coherence and temporal coherence? How will you determine spatial coherence? Give the condition for spatial coherence. With this, we come to the end of the lectures that we should see in the section on interference. Hereafter, we will move on to a series of lectures on diffraction. Thank you.